So we'll get started. Thank you everyone for joining us. My name is Arjun Beer. I'm the principal of our Atlanta office at Copeland Building Envelope Consulting. And I'll just be introducing our speaker for the day and just setting some overall context for how we're going to handle this webinar, and then I'll hand it off to Carmen. So first, I'd like to introduce our speaker. Carmen Prantil is a staff consultant in our Boston office. She earned her bachelor's degree at the University of Minnesota, Twin Cities, in building science and technology. And she specializes in solving building envelope problems in cold climates. And that skill set will very much be on display today. When not working, Carmen loves to be outdoors. She enjoys hiking, biking, and CrossFit. And yeah, she's an amazing contributor to our team, and I'm very excited for today's presentation. Before I hand it off, just want to let you guys know that if you have any questions, feel free to put them in the chat, and Carmen will take all of the questions at the end once her presentation is done. So with that being said, I'll put myself on mute, and Carmen, you can take over from here.
Yeah, thanks, Arjun, for that introduction. So, like you said, my name is Carmen Prantil. I am a staff consultant at Copeland Building Envelope Consulting, and today I'm going to be talking about the 4 barriers in a contemporary context. So to begin, just a little bit about Copeland. We are a team of 11 building nerds that can assist throughout the building life cycle, so from schematic design through construction and occupancy. And we offer a range of comprehensive building envelope services, from investigation to design to energy code compliance. So we'll dive right into why you got here today. This presentation is going to explore how to manage moisture by applying design considerations and quality assurance, quality control, QA/QC measures across all 4 barriers in exterior wall assemblies. And when I say moisture management, we're really looking at 3 types. So at the top of the podium, and let's be clear, this is not the podium you want to be on. It's kind of the gold is going to what's going to contribute perhaps the fastest to the most damage. So at the top we have water leakage. Second place is going to condensation, and still important, but finishing with bronze, is vapor diffusion. So what are the 4 barriers? You might also hear the term control layers, which for the purpose of this conversation, I'm just going to stick to the term barriers, but they mean the same thing. So we have water control, vapor control, air control, and thermal control. And while I'm listing 4 different barriers here, note that it doesn't necessarily have to be 4 unique materials. So some materials can be dual purpose or dual plus purpose, meaning that one material is actually serving as multiple barriers. So you might have something that is both an air and a water vapor barrier, both an air and a water barrier, or something like a thermal and a vapor barrier. And each of these barriers is in and of itself related to moisture movement. So that means that failure in any single barrier can compromise the entire assembly. So we'll take a closer look now at the function that each of these barriers serve, and we'll start with the water control. So this is essentially your first line of defense. It's going to prevent rain and bulk water entry. So examples of this can be water-resistant barriers. You might see something like Blueskin or Tyvek, or like the green of zip sheathing. It'll also include draining provisions, which are used in drained wall assemblies, which I'll touch on in a little bit. And it includes flashing. Next, we have vapor control. So water vapor diffusion at a super high level is when moisture molecules are able to pass through a material themselves. So think of it as like the ghost of moisture movement. And a vapor barrier is essentially a material that reduces that water vapor diffusion through materials. So examples of this can be sheet materials. You can have some elastomeric coatings that serve this purpose. Could be spray foam insulation or foil-faced insulation, specifically the foil facing of foil-faced insulation. And then we have air control. So the air barrier prevents air leakage And the reason that we care about this is because air carries water. So examples of air barriers can be, again, sheet products, fluid applied coatings, spray foam insulation, and rigid insulation, but specifically when it is taped or sealed at the seams. And then finally, we've got thermal control. So again, Arjun introduced me as loving cold climates, being in cold climates a lot. So this is my favorite because it's primarily used to maintain comfortable interior temperatures. But from a moisture perspective, it's also important because it contributes to condensation risk in assemblies. So example of these thermal barriers are going to be insulation. So things like batt insulation, spray foam insulation, or rigid insulation. And again, now that we've looked at all four barriers, I'm kind of just going to touch on that point again, that just because we have four barriers doesn't mean we have four unique materials. So spray foam insulation, for instance, I've now listed in vapor, air, and thermal. So it can, again, serve as two or more purposes in some cases. So this is really the crux that we're in now. So despite technology advances for buildings, contemporary buildings are increasingly vulnerable to moisture damage. And why is that? Well, to start, buildings today are more airtight and more insulated. So contemporary air barriers and sealing technologies have dramatically reduced natural air leakage, and we're adding more insulation to assemblies in aggressive energy efficiency efforts, which together, those two things contribute to reduced drying potential. And that means that when moisture gets into a wall assembly, it's taking longer for it to get out. And the bottom line of that is the wall assembly is just less forgiving. And on top of that, we have more complex designs. So you take the fundamental principles and you apply it to a rectangle windowless building, and it might be pretty straightforward. I actually probably wouldn't be giving this presentation today if that was all that we built, except architects are extremely creative, and they don't build rectangle buildings, right? So they design geometries that look like the Weizmann Art Museum here, or that have multiple different cladding materials. And then once it looks a little less soul crushing, they stick a ton of holes in it for natural light and maybe some mechanical ventilation to help with the whole more airtight, more insulated building trend that I just mentioned. So we have more complex designs. And then finally, we get to interior humidity levels. So the picture here that you see is actually from a natatorium. So this is the kind of humidity level we would look at in unique environments like natatoriums. But in a typical residential or office building or something like that, Modern Comfort tolerates about 35 to 45% relative humidity, which if we look at historic trends is increasing. And then we also have to factor in the changing climate patterns. So higher interior humidity, but then also the exterior conditions. Every summer since 1980, with the exception of two, we've had either warmer, wetter, or both exterior conditions. So ultimately, when we look at all of these contributing factors, we have challenges that we're not really getting away from, right? Because of energy efficiency portions of the code that are guiding us to build more airtight, more insulated, we're not changing our trajectory there. And quite frankly, we shouldn't want to. Architects, with the power of the left side of their brain, they're going to remain creative. They're going to keep me in a job. And the climate trends and comfort trends historically haven't changed. So knowing this, what we're kind of asking is if we can't go back, then how do we face the challenges that contemporary buildings pose? So we'll dive back into each barrier a bit deeper, and we'll start with water control. So I apologize if anyone is simultaneously eating lunch while watching this. I had to throw in some of the gore. So these are some of the consequences of water leakage that we've seen in exterior walls. So this is deteriorated framing members. I have two photos here that happen to be wood framing, but this can also happen with steel studs. You can get deterioration. You have wet or worse crumbling sheathing, right? Nobody wants oatmeal OSB. And you get deteriorated insulation too. So if it's interior insulation, meaning that it's between the stud cavity, like it's shown in these photos, that insulation deterioration is also happening likely alongside deteriorated framing members. So what design considerations can we take into account to avoid growing the library of photos that I just showed, right? So we'll start with the fact that there are two types of exterior wall assemblies that you can design. So the first is called a barrier wall system, which relies on continuity of watertight materials at the exterior surface. And this is essentially a single line of defense. There are no drainage provisions. So contemporary examples might be something like eaves without drainage, some metal panel wall assemblies like in a warehouse, or you can have precast concrete or block wall that has sealant joints and no weeps. And this type of assembly really functions on the principle that the barrier has to maintain 100% integrity. So any breaches that compromise, that barrier compromise the entire system. Water that gets in is not designed to get out. So it's basically an all or nothing protection, which comes with a lot of risk. And then you have a second type, which is called a drained wall assembly, which incorporates dedicated pathways that allow any water that enters the assembly to safely exit. So this would be most assemblies that you see today, something like brick veneer, curtain wall with weeps, siding installed over a drainage plane, things like that. And these walls essentially have two lines of defense. So the first being the cladding, which you can see here, and then the second being a water-resistive barrier that's installed at the backup of a drainage plane. And this assembly builds in redundancy, which is preferred. We like that. But it still relies on critical features and details like continuity of the water resistive barrier at the backup wall, or correct installation of flashing, which is again going to help direct the water that gets into the assembly out. So as I just mentioned, flashing is critical in drained wall assemblies, and its function is basically to collect the water that's in that cavity space and direct it to the exterior. And there are a few key things that we want to consider when it comes to flashing. The first is don't penetrate the horizontal surfaces of the flashing. Again, as I just mentioned, its primary function is to redirect the water out of the assembly. So any penetration on the horizontal is creating a literal hole, a pathway potentially for water to enter precisely where it's designed to collect. So we don't want to penetrate on the horizontal surface of the flashing. We want to fasten it on the vertical, like we see here. And then the second is that we don't want to reverse slope the flashing. So flashing has to slope outwards to direct water away from the building. Any inward slope, which you can see in this photo here, we've basically poured water on it and the water's running straight towards the building. Any inward slope like that creates a path that guides water toward the wall assembly as opposed to promoting water drainage away from the building, which is its intended purpose. You also want to provide end dams. So these are essentially raised edges at the end of the flashing that prevent water from flowing off of it sideways. Think of it like end caps on your flashing piece, right? So the water collects on the horizontal surface of the flashing. And again, if you've designed and installed it correctly, it should be sloped towards the exterior and flow out of the wall assembly. But it also has the ability to move laterally along the flashing too, right? So along like the length of it. And without proper end dams, what water can do is basically bypass the entire drainage system by just kind of flowing into the wall assembly at the ends if it's moving laterally. So we want to provide end dams and basically cap it so that that's not an option, right? If it moves laterally towards the end, it's hitting this end dam, it's not going into the wall assembly, it's still flowing out. Another thing that we want to do in design is to make sure that the documentation directs the contractor to shingle lap materials. Some people may also hear the term positive lap. In this context, they're referring to the same thing, but I'm just going to use the term shingle lap. So shingle lapping materials basically means that each layer overlaps the one below it so that when water flows over it, it flows over the joints, not behind them. So you can see an example here with the little green check mark. That's a shingle lap. And the opposite is called a reverse lap, which we see here with the little red X. And that's when the lower material is installed kind of overlapped on the upper one. And this can be bad because if the lower material begins to peel away, it can do something called fish mouth, where you basically have like a little bit of a gap between the layers. And then any water that's running down the drainage plane with gravity can be directed into the wall assembly behind that lower material, right, instead of guiding it out and away. So when you have reverse laps, you have to continuously terminate the lap with sealant or with mastic. And these continuous terminations, while they are a possibility, they rely on the workmanship of the sealant installer. So if you have a reverse lap and the sealant is installed messily or in a manner that's not continuous, you basically provide a pathway for water to get in. So we want to make it easy for ourselves, work with gravity, call out shingle lapping materials. So moving beyond design to quality assurance and quality control during construction, we can do water leakage testing, various forms of it, and we can do construction administration to verify that the barrier is continuous. But along with this QA/QC, on the design side, we want to specify the exact water leakage testing requirements in the documentation. So this includes things like including the approved test method, the number of tests, the test locations where we want this so that we can actually confirm it in the field. All right, we'll hop over now to vapor. So vapor is not visible in the way that bulk water is, and so it's a little harder to wrap our head around. So I'm going to go back to some basic terminology that we can essentially build on for this section. So first we have relative humidity, which is the measure of an air's moisture content at a specific temperature. And this is important because warm air can hold more moisture than cold air. So let's say 40 degrees can hold something like 6 droplets of water, and 90 degrees can hold something like 24 droplets of water. And so 50% relative humidity at 40 degrees, we're talking the quantity of water is 3 raindrops, and 50% relative humidity at 90 degrees is 12 raindrops, again, because that 90 degrees can hold more than the 40 degrees. So this is really just showing that relative humidity has no meaning isolated, right? If I just said 50% relative humidity, am I talking about 3 raindrops, 12 raindrops, a different number of raindrops? We don't know. So to understand how much moisture we're talking about, we really have to place relative humidity in the context of temperature. And then we have dew point. So East Coasters will appreciate this slide because of the Duncan, but dew point temperature is the temperature at which condensation forms. So if any surface falls below it, you'll see condensation or water droplets. So a common thing that we see this on is something like an iced beverage container in warm weather, because again, the surface of that container is colder. So similar to ambient temperature, which is the temperature that we would feel on any given day, right? It's like what you're perceiving right now as you're sitting in a room or if you're outside. And so similar to that, the dew point depends on the day and the season. So there's a dew point temperature every single day. All right, I gave you like a 5-minute terminology crash course. So now we'll just apply those quickly to vapor drive. So vapor moves from higher pressure environments or higher concentrations to lower pressure environments or lower concentrations. And in buildings, this typically means from warm to cold, because again, warmer air holds more moisture, so higher concentration. And this is like the world's way of, again, trying to like create equilibrium. And this is important for us to understand vapor drive because of climate. So in a cold climate in winter, vapor drive is going to be from the interior to the exterior because we are heating the interior, we're humidifying the interior, and it's snowy and cold outside. And if we travel to a hot and humid climate, the vapor drive is going to be in the other direction from exterior to interior because again, we are dehumidifying the interior space. We're putting something like an air conditioner in to cool it. And on top of this, we have to also consider that even the season, summer versus winter, can change the vapor drive direction because again, if you're heating or cooling an interior space and how that is relative to the exterior temperatures and vapor conditions is going to change. So when we're designing, essentially what this comes down to is we really have to consider the climate. If vapor flows in different directions, depending on the climate, you have to be intentional with where you place your vapor barrier in the wall assembly. And the bottom line of this is don't place it on the wrong side of the assembly. So if we have vapor drive from exterior to interior and we place a vapor barrier on the interior of the wall assembly, we will be catching and trapping moisture in our walls, likely adjacent to materials like batt insulation, which are not, moisture tolerant. And this can be problematic in any environment. You don't want to place it on the wrong side in any environment, but it's far less forgiving in hot and humid climates, again, because warmer temperatures are going to be carrying more moisture. So from a design side, think about the climate that you're building in, think about the vapor drive direction in that climate, and then place the vapor barrier on the right side of the wall assembly for that climate and for that vapor drive direction. And after I just got through talking about how you want to place it on the right side, I'm now going to kind of back up and just discuss the risk of designing wall assemblies with interior vapor barriers, period, whether it's in a wall assembly that's the right side or the wrong side. So interior vapor barriers can be materials like poly, like vinyl wallpaper, like oil-based paints, the foil facing, again, of like foil-faced rigid insulation. And like I just mentioned, we'll definitely run into problems if we're placing it on the interior when that's the wrong side of the assembly for the climate that we're building in. But even in climates where an interior vapor barrier can work, it comes with risk because it blocks the essential drying path to the interior. So this can hinder early warning signs of moisture in the assembly, which are observed by occupants at the interior. So these early warning signs aren't going to be something like bulk water movement. Like it won't be, a leak or a puddle on the floor. We're going to be looking for things like staining of interior finishes, bubbling or peeling paint, things like that. And worse than just putting a vapor barrier on the wrong side or putting it on the interior or something like that is something called the vapor trap. So this is essentially when you have an exterior vapor barrier and an interior vapor barrier. And what this does is it traps moisture so that it can't dry in either direction. And if there's no chance for the assembly to dry in either direction, then if and when water gets in, there's essentially no forgiveness for it to dry out, leaving your only option as really cutting open the assembly and replacing the wet and damaged materials. And we want to avoid that situation. So think about the materials that you're specifying so that you're not creating a vapor trap. So for example, if you are specifically designing with an exterior vapor barrier, then think very critically about the interior. Maybe you have an interior designer or something. Make sure that they're not like planning to put vinyl wallpaper on the gypsum board or something like that, because then again, you're going to be creating a vapor trap in your wall assembly. Right, so how do we do it? We look at something that has been working for centuries. Some of you may have heard of this. It's called the perfect wall. And if not, the idea behind it is basically that you want cladding at the exterior, and then your four barriers, and then structure at the interior. And this wall assembly, this perfect wall, works in all climates. So it's going to work in the cold climate, it's going to work in the hot, humid climate, it's going to work in everything in between. So for proper vapor design, let's start with this idea of the perfect wall. And then in cold climates where we need more insulation, we can split the insulation. So we can have insulation on the exterior and then also in the structure, so between the studs. And you have to be careful when you're splitting insulation too in cold climates. And that's because the ratio matters. So how much you're putting on the exterior relative to how much you're putting in that structure, in the stud cavities, really matters, which kind of leads me into the quality assurance, quality control that we can do for the vapor barrier. So for this, we can do things like a WUFI model, which is a hygrothermal model. So for example, this was a project where the architect came to us during design and they said, hey, this is a wall assembly that we've designed and we split the insulation. And we want you to verify that this wall assembly isn't going to run into vapor drive or condensation moisture issues. And so we took their wall assembly and we simulated it in WUFI. And we basically looked at the heat and the moisture transfer across the entire assembly over the course of several years. And what this told us, as you can see here down in this graph, was that the maximum relative humidity was about 70%, which is a safe number because it's below 100% and it's not close to 100%. So 100% relative humidity is where the air is fully saturated. So you can think about this as like basically when the air starts like dropping water, right? So this was a quality assurance check that we were able to perform in design development to confirm that the proposed assembly before it was actually built wouldn't be conducive to things like moisture issues from vapor. All right, 2 down, 2 to go. So we will move on to air. As I mentioned previously, the reason that we care about air is because air carries moisture. And what's really critical to this is that in order for air to carry moisture, there has to be a pathway. So unlike vapor diffusion, which again I kind of referenced as like the ghost of moisture movement, it moves through materials, air needs some sort of void. And when I say it needs some sort of void, we're really talking about like a discontinuity in materials that act as the air barrier, right? So you can't have a hole in your air barrier because then air is just going to be able to move straight through that hole. And compared to vapor diffusion, air carries a lot more water. We're talking like 50 to 100 times more. So we can see that kind of in this comparison. So down here, we've got vapor diffusion moving slow and in small amounts through a material. When you've got air movement and a hole, it's really moving in higher concentrations and quite quickly. So if you have an air leakage problem, meaning you have a void that air can travel through in your wall, you've also got a potential moisture problem, and one that can cause much faster damage than vapor does because of the concentration. And that air carrying moisture is a huge component of condensation. So what's important to know about condensation is that it's not a leak, right? So you start with warm, moist air, and it meets a cold surface within your wall assembly. And when I say cold surface, I'm specifically talking about something that is below the dew point temperature, right? So a temperature that condensation would start to form on it. It doesn't necessarily mean that it has to be like below freezing or anything. It just has to be cold in the sense that it's below the dew point temperature. And this is really where air becomes the catalyst, right? Because you wouldn't have warm, moist air meeting this cold surface in the wall assembly without air movement or some sort of void, like I just mentioned. So once you have that warm, moist air meeting the cold surface, you get water droplets forming, again, because it's meeting something that's below that dew point. And that's happening likely somewhere in the wall assembly where you can't actually visibly see it because it's somewhere. It's not the interior surface, it's not the exterior surface, it's somewhere in the middle, you can't see it. And then moisture will start to accumulate there in small amounts daily, and this builds up over time, and you essentially get deterioration that occurs within the wall assembly that you don't notice until much later when it starts to grow and reach, a level that you're beginning to see either on the interior or the exterior. And similar to vapor diffusion, the early warning signs that you would look for with this kind of condensation in wall assemblies would typically be seen on the interior, and you'd be looking for things like bubbling or peeling paint, staining of interior finishes, things like that. So we'll take a little bit of a closer look at parapets specifically, since these are particularly tricky when it comes to condensation. So parapets are intrinsically difficult for a couple of reasons. Number one, they are exposed to the elements on three sides. So this means more surface area, seeing more environments, interior and exterior. Number two, they're often poorly insulated. And number three, it's a complex transition between the wall and roof assemblies. And this transition point is a common place that we see discontinuities in the four barriers. So in part, one of the reasons that we see this and why it's tricky is because the roof assembly and the exterior wall assembly are typically handled by two different trades, right? So there needs to be some sort of coordination between the two trades to make sure that we're retaining continuity from one assembly to the next. So there are essentially two types of parapets that we see. There is a parapet type that is within the air barrier. Some people might refer to this as a conditioned parapet. And you essentially have the exterior wall running all the way up, right? And this parapet is really seeing the interior conditions. It thinks that it's a part of the inside. And then you have the parapet type that is outside of the air barrier. Some people might refer to this as unconditioned. And so you have, the roof deck coming across and the parapet kind of like sitting on top of that. And this is a little bit more like the parapet is outside, right? So it's not necessarily seeing the conditioned space. And so here's the problem. We have the parapets within the air barrier, right? The conditioned parapets. Let's say we have an interior finish, something like gypsum board. That's not an air barrier. And because again, this design is designed in a way that it thinks it's conditioned space, right? So the warm air can travel up from the inside, because again, that gypsum board's not an air barrier. And if we don't have insulation on the top, or maybe the interior face of the parapet, so what I've highlighted here in red, then those surfaces are confused because they're inside the conditioned space, but they're really experiencing and feeling conditions of the outside, right? Like those surfaces are going to be cold in the winter. So what you have is you have this warm air that's traveling up or traveling in, and it's going to hit, say, a steel HSS member or the sheathing, and those are cold, and condensation is going to form. So that's what we're looking at really as a problem on the conditioned parapets. And if we look at the parapet that is outside of the air barrier, right, the unconditioned parapet, I've highlighted the vapor barrier in blue. And again, you can still get some of that vapor drive up through that roof deck. You have these cold temperatures at the HSS steel or something like the sheathing. And when you have that warm air traveling up, hits those surfaces, boom, water. So, okay, great. We've highlighted red flags. We have water everywhere. What do we do? So we have a couple of potential solutions. Solution one is tying the vapor barrier of the roof assembly in with the vapor barrier of the exterior wall assembly. But something to note about this approach is that it can require more consideration with construction sequencing because, like I said, typically you have the roof assembly as one trade and the exterior wall assembly as a different trade. And so those two trades need to coordinate to make sure that that continuity is actually present and that you don't have some sort of gap because again, that gap, all it takes is one void, right, for the air to be able to move through. And solution one might also be a little bit more difficult in a retrofit solution or an existing building, depending on the repair scope of work that you're doing, right? So if you're not opening all of that up, it can be a little bit more tricky. So an alternative option is to look at something like solution two, where we're adding closed cell spray foam right here at the base of the parapet. And if you remember back to the introduction on vapor barriers, spray foam is a vapor barrier. And so this basically creates a continuous vapor barrier between the parapet and the interior conditions. And that's really the key to parapets is you want to keep the inside, inside, and you want to keep the outside, outside. So now that we know more about the challenges of air barriers, we can look at some design considerations for it on exterior walls. And the reason I also highlighted water here, it wasn't a slide error, is because there are considerations here that I'm going to go through that can really be applied both to air and water control barriers. So we'll start here with barrier continuity. So one of the essential considerations in design is to make sure, again, both the air and water barriers are continuous. And the current energy code actually requires air barriers to form a complete uninterrupted envelope around the building's conditioned space. And this can be achieved in two ways. It can be achieved through detailing continuity of all air barrier assemblies and connections, or it can be achieved through performance testing, which I'll touch on in a little bit. But if you want to do it on the design side, right, you want to detail all the continuity of all the air barriers, then one way engineers and architects can check this in design is with something called a pen test. So you take a detail or a series of details. So what I've done here is I've stacked kind of 3 details from grade to roof. And what you can do is you can trace this detail and follow the control layer. So what I've done is in orange, I've highlighted the air barrier in this assembly and I've traced it all the way, from roof to grade. And you would want to do this around your entire building envelope, right? Line up all of your details. And you want to trace this with your pen in a certain color or whatever. And if you have to lift your pen at any point, then you've identified a discontinuity. And this is particularly important to do, like as a pen test, because again, remember that the air barrier isn't just one material, right? So if you're going from one air barrier material to a second, are you making a jump that is going to cause a discontinuity? You want to be able to trace it and have continuity with your pen line. And so if we look at this particular project, right? So this is actually what I'm picturing here. This metal panel right here is this kind of black void. I don't have a picture with the metal panel installed yet, but that's kind of the idea, and the soffit is beyond in this detail. So if we look at this detail, we'll notice that I actually traced the air barrier to return behind the exterior insulation and behind the metal panel rather than running in front. And you might ask the question, like, why not just wrap the whole soffit beyond the metal panels in an air barrier? And this lower photo kind of hints at it, which is these holes that you can see, which are for exterior lighting fixtures. So that would cause discontinuities if we were to wrap the soffit and have the air barrier there on kind of like the outside plane. So we return it instead so that we can keep that continuity. Um, and so this also kind of points out the fact that the pen test will have limitations, right? So things like penetrations for exterior lighting fixtures might not be shown on the drawings. Or if we look at this upper photo here, things like end conditions. So this particular project had one that what we were designing tied into an existing building or an existing structure. So tie-ins like that might not be caught in a pen test simply because the pen test is really limited to 2D space, like on a 2D detail. And so at end conditions, you have to make sure that you're creating a tie-in or a termination of the air barrier. We can see it here in blue, just a little bit where it's tying in with the existing structure. And we have to think of this kind of like an end dam, but for the air barrier instead of for flashing. Because again, we want to maintain that continuity. So like bottom line of this is pen test, great tool to have, but be mindful of its limitations and some of the other factors that you have to consider on top of it. And for air barrier, quality assurance, quality control, we have a whole toolbox of qualitative and quantitative tests that we can run. So some of the qualitative tests include things like the bubble test. It's going to sound silly when I explain it, but you essentially put like a soapy liquid where over like a potential discontinuity, maybe at a transition point, something like that. And then you're going to put this like bowl over it that's going to apply negative pressure. So it's essentially going to suck on the air barrier. And if you see a bubble, what does that mean? Basically, you would have air movement, right, that's creating that bubble, which means that you have a discontinuity. Beyond the bubble test, you can also look at things like an IR camera with pressure. So at night, when it's cold and the building is pressurized, the leak would appear as warm interior air passing through to the outdoors. Or you can do something like smoke testing with pressure to visually see air movement. And beyond the qualitative testing, you can also do quantitative testing. So you can do things like field testing of specified products or whole building air leakage testing, which, as I mentioned before, current energy code requires the air barrier to have that complete uninterrupted envelope around the building's conditioned space. So you can achieve that, like I said, by detailing or through performance testing. So this whole building air leakage test is one pathway for compliance with the current energy code. And similar to what I mentioned in the QA/QC portion for the water barrier, you want to explicitly specify the testing that you're going to require in your documentation. So test method, number of tests, test location, things like that. And there are resources for finding that information. You can find recommendations for testing in manufacturer literature or applicable ASTM standards. So I've conveniently located them on this slide if anyone is quick enough to snap a photo. And we've made it to the last barrier, which is going to be thermal. And as it relates to moisture movement, what's particularly important is something called thermal bridges. And so at a very basic level, a thermal bridge is a portion of a building assembly that heat can easily escape through because the material conducts heat well and it's cutting through the thermal barrier or the insulation. So good conductors are materials like metals or concrete. And so common thermal bridges we see, right, are steel stud walls without exterior insulation, right, because it's got to cut through the thermal barrier. So if we look at a steel stud wall, no exterior insulation, that's a common thermal bridge. We've also got window frames and edges. So if you've ever like felt a window frame and it's been really cold and you're feeling it on the interior, but it's winter outside, that's a thermal bridge, right? Because the heat is essentially escaping through that frame or through the window edge. And then things like balcony projections, right? Because those are projecting out of the structure. So we'll look at a case study really quick of a recent peer review that our team did at a local restaurant. So this was a new construction project. It was a restaurant space located above a below grade parking garage. So we had the unique condition that we had conditioned space located directly above unconditioned space. And the client here engaged us super early to do thermal bridging analysis with the goal to limit thermal bridging in order to pass Massachusetts stretch energy code. And so we use tools like thermal modeling to gauge the thermal bridging potential in several details during early design. So this is the first option that we put together. We put split insulation in the wall assembly and carried the exterior insulation down the foundation wall. And when we modeled it in therm, you have a significant amount of thermal bridging at the slab, right? And as I mentioned before, concrete is a really good conductor. So that was happening there. So the red is really like the heat, right? And the blue or purple is colder. So we have a lot of heat traveling and escaping thermal bridge. And so then we ran a second model, which used split slab insulation between the restaurant and the garage spaces. And a split slab, for those who don't know, is basically when you have a bottom layer of concrete poured, then you install insulation on top of it, and then you do a top layer of concrete to complete the slab. And so what this does is it creates a thermally isolated upper portion of concrete separated from the ground, or in this case, separated from the unconditioned space by that insulation layer. And so when we detailed this in therm, we got significantly less thermal bridging, right? Like that slab stayed purple because, again, that insulation was acting as a thermal break. And so this project moved forward with this option, but critical to the success of this project was the point at which we were engaged, right? We came in very, very early in the design stage, and this case study really exemplifies the tools that we can use during schematic and early design to inform good design decisions before we're locked into certain assemblies. We can catch concerning conditions early when there's still a lot of pivot room, which can save a ton of time and a ton of money. And this really brings us back to the fact that code today is pushing us more actively back towards this perfect wall assembly, right? Which, as a refresh, it's cladding on the exterior, then you've got your 4 barriers, and then you've got your structure or your framing. And the reason that this works in all climates is because the perfect wall essentially operates on this principle of being an environmental separator. So like I said before, we want to keep the outside out and the inside in. So the best place for the 4 barriers is to locate them on the outside of the structure in order to protect the structure. So things like expansion, contraction, corrosion, decay, a lot of bad things, a lot of expensive things are functions of temperature and moisture. So all of the control layers go on the outside, or split insulation so that at least some is on the outside, and keep the structure from going through the temperature extremes and protect it from the water in its various forms, and life will be good. So I want to wrap up by stepping back and kind of looking at the 4 barriers holistically and together, because there are some design considerations that we want to look at all 4 as a whole. And so one of these things that is imperative to think about on the design side is the actual constructability of what you're designing, right? So there are days that I've shown up on site and I've literally wanted to like get this tattooed on my forehead. But if I explain it enough now, maybe I can save myself that. So what do I mean by constructability? So to start, coordinate in design. So projects have architects, right? They have building envelope engineers or consultants. They have structural engineers. They have MEP engineers. But when every trade is tunnel visioned in their own design and you don't coordinate, you end up with things like this photo. Don't end up with things like this photo, right? We had a structural engineer installing a support column here, and it wound up being inches from a building corner that needed through wall flashing, and then some roofer got the fantastic short straw of roofing in between these two in that little nook and cranny. So talk it out. We're friends. Catch it in design, right? Work and coordinate in design. Building on that, and particularly important when you're working on repairing, like repair design, or when you're working with an existing building, is draft to scale. So on an existing building, you should always field verify the space constraints that you have present, and you should depict those accurately in your details, again, so that the design coordination can be accurate. And related to both of these is considering spatial constraints. So I'm going to go back to this photo that gives me nightmares. Did we consider if the space was accessible for the required installation method? By the looks of it, no. Similar common example is, let's say, the structural engineer is installing dunnage to go on the roof. Coordinate that with the architect or the engineer. What is the roof assembly height? That dunnage is going to be installed first, right? And you're going to have to fit a person under it to install the roofing. So how small is your roofer? Think about space. And then finally, consider trade coordination. So this is similar to design coordination, but on the construction side. So you want to identify which specific trades are responsible for each component for the purpose of minimizing handoff between trades where it's possible, right? So don't make the sequencing such that it has to go back and forth from trade 1 to trade 2, and then back to trade 1, and then back to trade 2, or maybe to a trade 3, because these handoffs are prime examples and prime time for making mistakes, not communicating well, and resulting in discontinuities. And then when it comes to specifying materials, you really want to consider material compatibility. So incompatibility can be materials that are chemically incompatible. That's what we typically think of. It can also be materials where they're used in instances where they're installed improperly. So if you think about, let's say, a metal parapet, the membrane that goes under that metal parapet should be high heat, right? Because when you have the sun beating down on it, that metal is going to get super hot. And it's going to transfer some of that heat to the membrane. You want a membrane that chemically is, tolerant to higher temperatures. If you put a normal membrane under there, one that doesn't have high heat capabilities, then when that sun beats down and the parapet gets very hot, it can lead to things like melting of the membrane, which we see here. And so using incompatible materials can lead to things like, chemical breakdown. It can lead to things like loss of adhesion, brittle materials, overall just reduced service life, but a big red flag to owners, and what should certainly be considered as a designer as well, is that using incompatible materials can also void your warranty. Okay, so that was a lot of talking, and we're coming up short on time. So I will kind of wrap this up with a couple of key takeaways. So if you remember one slide from this presentation, I guess sear this one into your brain. So first and foremost, maintain continuity of the 4 barriers, right? So think about it in design and then verify it through quality assurance, quality control. Number 2, explicitly specify your testing requirements. So again, things like test locations, number of tests, approved test method, and there are resources and manufacturer data sheets or ASTM standards that can help with this. So you're not alone in having to just come up with it. And then finally, consider constructability. Again, I don't want to get it tattooed on my forehead, so please just remember it. The success of a building doesn't live on paper, right? So make sure it can translate from your design into the real world. All right, that's all I have. Thank you for listening. I will open it up for questions now. I'll look in the chat. I also know that was a lot of information to digest and cover quickly. So I've included my email on the slide here. You are welcome to shoot me any questions that are nagging you later today, later this week, anything like that.